In the earlier videos, we defined chemical kinetics as the following. Chemical kinetics is the study of reaction rates, that is, how fast the reactions proceed, and their mechanisms. So far, we have discussed what is a reaction rate and how the reaction rate depends on the concentration of the reactants. We also discussed that the equation that connects the reaction rate and concentrations is called the rate law or rate equation, and we have also learned how we determine the rate law of a reaction from the experimental data. Next, we will learn how to use the rate law to propose the pathway or a mechanism for a given reaction. Reactions usually proceed through a series of steps. The sequence of steps that form the overall equation is called as the reaction mechanism or reaction pathway. For example, consider the following reaction. Nitrogen dioxide gas reacts with carbon monoxide gas to form nitrogen monoxide gas and carbon dioxide gas. The experimentally determined rate law for this equation is rate is equals to K times concentration of NO2 to the power 2. That is, the reaction is second order with respect to NO2 and zero order with respect to carbon monoxide. Now, even though the carbon monoxide is a reactant of the equation, the reaction rate does not depend on the concentration of carbon monoxide. Why? To answer this question, we need to understand the mechanism or the pathway of the reaction. It has been proposed that this reaction proceeds in the following mechanism. In the first step, a nitrogen dioxide gas molecule reacts with another nitrogen dioxide gas to form a nitrogen trioxide gas and nitrogen monoxide gas. In the step 2, the nitrogen trioxide gas molecule formed in step 1 reacts with carbon monoxide to form nitrogen dioxide and carbon dioxide. If we add step 1 and step 2, we get the overall reaction equation. The species NO3 is formed in step 1 and consumed in step 2, and therefore it does not appear in the overall reaction equation. These kind of species are called as reaction intermediates, and the individual steps of the reaction mechanism are called as elementary steps. Let us learn a little bit more about the elementary step. An elementary step describes the molecules that must collide to produce the products of that elementary step. It is treated as an individual molecular event. For example, the elementary reaction 1 in the previous slide means that an NO2 molecule collides with another NO2 molecule to form NO3 and NO. One of the biggest differences between an overall reaction and elementary reaction is the following. For an overall reaction, we kept emphasizing that we cannot write the rate law from the coefficients of stoichiometric equation. The rate law has to be determined experimentally. For an elementary reaction, however, we can deduce the rate law directly from the reaction stoichiometry. The rate of an elementary reaction is equal to the product of a rate constant and the concentrations of reacting species, each raised to a power which is equal to its stoichiometric coefficient. For this elementary reaction, the rate law is equal to some constant K times NO2 to the power 1 times NO2 to the power 1, which is equal to K times NO2 power 2. Note that we can only do this for an elementary reaction or an elementary step of an overall reaction. We use a term called as molecularity to describe the elementary reactions. Molecularity is defined as the number of species that must collide to produce the products of the indicated elementary reaction. Based on the molecularity, elementary reactions can be classified into three different categories. 1. Unimolecular reaction. An elementary reaction that involves only one reactant is called as unimolecular reaction. For example, the reaction A gives products. There is only one molecule involved in this elementary step. The rate law for this elementary step is rate is equal to K times concentration of A. Again, note that we deduced the rate law from the balanced stoichiometric equation only because this is an elementary reaction. If an elementary reaction involves collision of two molecules, then it is called as a bimolecular reaction. The two molecules colliding can be of same type. For example, A plus A gives products, or the two molecules colliding could be of different types. For example, A plus B gives product. Since these are elementary steps, we can write the rate law directly from the stoichiometric equation. For the first type, the rate law is rate is equal to K times concentration of A to the power 2. And the rate law for the second type is rate is equal to K times concentration of A times concentration of B. The third type is called as a termolecular reaction. If an elementary reaction involves a collision of three molecules, then it is called as a termolecular reaction. The three molecules that collide can be in the following combination. A plus A plus A gives products, or A plus B gives products, or three different molecules, which is A plus B plus C gives products. Just like before, we can deduce the rate laws for these elementary steps directly from the balanced stoichiometric equation. Termolecular elementary reactions are quite rare because the possibility of three molecules colliding at the same time in the correct orientation is very, very small. Now, let us go back and look at the proposed mechanism for the reaction we discussed earlier. The reaction proceeds in two elementary steps. Let us now write the rate law for each of the elementary steps and also write down the experimentally determined rate law for the overall reaction. For elementary step 1, the rate law is rate is equal to K times concentration of NO2 to the power 2. For step 2, rate is equal to K times concentration of NO3 times concentration of CO. The constants for step 1 and 2 are different. The experimentally determined rate law for the overall reaction is rate is equal to K times concentration of NO2 to the power 2. One of the important requirements for a mechanism to be valid is that the rate law of the proposed mechanism must agree with the experimentally determined rate law. Now, how do we deduce the rate law of the overall reaction from the proposed mechanism? To understand how we deduce the rate law from the proposed mechanism, we need to introduce a concept called as rate limiting step. In a multi-step pathway, each elementary step proceeds at a different rate. The slowest step in the multi-step pathway is called as rate determining or rate limiting step. This is basically the bottleneck of the reaction, and the rate of the overall reaction is equal to the rate of the slowest or rate determining step. For this reaction, based on the proposed mechanism, the first step is the slow or rate determining step, and the second step is the fast step. What it means is that the rate of formation of NO3 is slower than the rate at which it is consumed in the second reaction. In other words, as soon as NO3 is formed by step 1, it is completely consumed in step 2. Therefore, the rate of overall reaction is equal to the rate of the first step or the rate determining step, which is equal to K times concentration of NO2 power 2. Note that the rate law derived from the mechanism is same as experimentally observed rate law, which means that this mechanism could be reasonable or valid. Let us discuss a little bit more about the mechanism and what makes a mechanism valid. A mechanism is a hypothesis, which means we cannot prove that it is correct. We can only say that the mechanism is consistent with the experimentally determined rate law. A valid mechanism must always meet the following criteria. 1. The elementary steps must add up to produce the overall balanced equation. And 2. The mechanism must correlate with the experimentally determined rate law. So, scientists usually determine the rate law of a reaction from experimental data and then come up with a mechanism that agrees with the experimentally determined rate law. It requires a lot of experience for someone to come up with a valid mechanism. Let us look at some more examples of different mechanisms. This is an example of a mechanism with a slow initial step. The overall reaction is 2 moles of nitrogen dioxide reacts with fluorine gas to form 2 moles of NO2F. The experimentally determined rate law is rate is equal to K times concentration of NO2 times concentration of F2. The proposed mechanism for this overall reaction is the following. In step 1, nitrogen dioxide reacts with fluorine to form NO2F and F gas. In step 2, nitrogen dioxide gas reacts with fluorine atom to form NO2F. The first step is the slow or rate determining step, and the second step is the fast step. Let us now see if the two requirements of a mechanism are met. If we add step 1 and step 2, we do get the overall reaction. Next, let us see if the mechanism agrees with the experimentally determined rate law. For step 1, the rate law is rate 1 is equal to K1 times the concentration of NO2 times the concentration of F2. For step 2, the rate law is rate 2 is equals to K2 times concentration of NO2 times concentration of F atoms. This step 1 is the slowest step in the reaction mechanism. Therefore, the rate of the overall reaction must be equal to the rate of the slowest step, that is step 1. So, overall rate is equal to K times concentration of NO2 times concentration of F2. The rate law deduced from the mechanism is same as experimentally determined rate law. Therefore, we can say that the mechanism is a reasonable or a valid mechanism. Let us now look at an example of a mechanism with a fast initial step and slow second step. The overall reaction is 2 NO gas reacts with 1 O2 gas to form 2 NO2 gas. The experimentally determined rate law for this reaction is rate is equal to K times concentration of nitric oxide to the power 2 and oxygen gas concentration to the power 1. That is, the reaction is second order with respect to NO and first order with respect to oxygen gas. And the proposed mechanism for this reaction is step 1, 1 NO reacts with 1 O2 to form NO3 gas. This is a fast step and it is also a reversible step. In step 2, the NO3 gas reacts with NO gas to form 2 NO2 gas. This is the slow rate determining step. Let us now check if this is a valid mechanism. If we add the two elementary steps, they will add up to give the overall balanced equation. So the requirement 1 is met. Next, let us now see if the mechanism agrees with the experimentally determined rate law. First, let us write down the rate law for both the elementary steps. As we can see, the step 1 of the reaction is a reversible reaction, which means we can write down the rate law for both the forward and reverse reactions. The rate law for the forward reaction is rate 1 forward is equal to K1 times concentration of NO and concentration of O2, which are the reactants for forward reaction. The rate law for the reverse reaction is rate 1 reverse is equal to K minus 1 times the concentration of NO3 power 1. As we can see, for the reverse reaction, the NO3 gas is the reactant. Next, let us write down the rate law for step 2. Rate 2 is equals to K2 times the concentration of NO3 times the concentration of NO. Since the second step is the rate determining step, the rate law for the overall reaction should be same as the rate law of the second step. Let me write that down. Rate overall is equal to rate 2 is equal to K2 times concentration of NO3 times concentration of NO. This rate law has concentration of NO3 term in it, which is not the reactant of overall reaction. It is an intermediate which is formed in one of the steps and consumed in the others. And as we discussed earlier, the rate law is the relation between the rate of the reaction and concentration of the reactants. And NO3 is not the reactant for the overall reaction. Therefore, it cannot be in the overall rate law. Therefore, we need to replace this term with a reactant concentration. What we are going to do is use the rate laws of the first step and calculate the concentration of NO3 from them. And then we substitute the concentration of NO3 in the above equation. Let us look at step 1. When equilibrium 1 has been established, we can say that the forward reaction rate must be equal to the rate of the reverse reaction. And we know that the rate of forward reaction is equal to K1 times concentration of NO times concentration of O2. And the rate of reverse reaction is equal to K minus 1 times the concentration of NO3. Next, we rearrange this equation to isolate concentration of NO3 on one side. We get concentration of NO3 is equal to K1 over K minus 1 times concentration of NO times concentration of O2. Let us substitute this in the above equation. Rate overall is equal to K2 times K1 over K minus 1 times concentration of NO times concentration of O2 times concentration of NO. Let us assume that the product of all these constants K2 times K1 over K minus 1 gives another constant, and let's call it K. So we can write the simplified form of the rate equation as rate is equals to K times concentration of NO to the power 2 times concentration of O2. This rate law, which is deduced from the mechanism, is same as experimentally determined rate law. Therefore, we can agree that this mechanism is a reasonable mechanism.